Hello everyone, welcome to this video. Today's topic is combined motion. Combined motion means one body will have translational motion as well as it will have rotational motion. Let's see. Suppose this is a body, its center of mass is at the middle point. So this is the center of mass. If any force I apply and if the line of action of this force on this body is coinciding with the center of mass point, then this body will have purely translational motion. If the mass of the body is m, if I apply the force in such a direction that the line of action of the force is matching with the point that is the center of mass, then this body will have only the acceleration, that is F by m. Or suppose if I apply any impulse on this body, suppose if I am applying impulse of j, instead of F I am applying impulse of j. What is impulse? Impulse will change the momentum of this body. So eventually what will happen? This will get some velocity. This m mass will get some velocity in the direction of the impulse. And if the direction of the impulse is coinciding with the center of mass point of this body, it will have purely translational motion. If I apply j impulse on a body of mass m and if the line is coinciding with the center of mass, then the velocity it will get, it is basically j by m. Or basically we can tell that impulse is going to change the momentum of this body, mv minus initial momentum, that is 0. So v is j by m. This is the case of purely translational motion. Now, if a body is like this and if the center of mass is here, suppose right now I am applying the impulse of j at distance x from the center of mass, and the length of the body is L and the mass is m. So what will happen in this case? In the first case, in the direction of the impulse, this body will move. So after some point of time, if this is at t equal to 0, after some point of time, this will have the velocity of j by m, and this will maintain at time t, it will maintain the same orientation. So that means it will not rotate with respect to its center of mass. So this is a completely translational motion. Now let's come to the second case. In this case, the impulse is applied at some distance from the center of mass. Let's see, this is a rod. I am applying my impulse here on the middle. It will move like this. It will not rotate. It will move like this only. So in the second case, if I am applying some impulse at this point, so see, it will rotate and it will move forward. So this is a case of combined motion. Now, due to the application of this impulse, this body will move with some velocity, linear velocity. So that velocity is basically j by m. This is the translational case of the combined motion. Now, this will have another kind of motion, that is also rotational motion. Why? Because see, j is applied at some distance from the center of mass. So this is the basically the momentum. We can tell that, okay, impulse means we can tell that momentum is applied on the body. This momentum is not coinciding with the center of mass. This momentum is at some distance x. So with respect to the center of mass, it is having some angular momentum, or due to this j, some angular momentum will be changed for this body of mass m. Now see, what is the angular momentum I am applying, or we can tell that angular impulse I am applying due to this j, because if I apply impulse at some point which is not coinciding with the center of mass, it will create the impulse, or we can tell that impulsive torque also we can tell. So angular momentum we are applying, that is x or r cross p But here suppose it is perpendicular, so we will write x into j or j into x. That is the angular momentum change of this body. So let's say it will rotate with angular velocity of omega. Now, whenever there is a rotation, the property of this body will be moment of inertia. Angular momentum is I into omega for this body. So omega will be basically jx by I. Now what is the I? I is the moment of inertia with respect to the center of mass. So we will write ICOM. Now let's visualize how this body will move forward. So combined motion. First part will divide, that is translational motion. Trans I am writing, and one is rotational motion. So translational motion, if we divide the motion into two parts, one part of it will make it move with velocity v, that is equal to j by m, and while moving it will rotate. It will rotate with some angular velocity, that is jx by I com. IC I am writing. So the motion of the body is the summation of these two motions. It will go forward with rotation. But the center of mass will travel with this velocity and the entire body will be moving like this. So if I apply J impulse here, it will move like this and it will go forward. The velocity will get by this impulse by the mass, and the angular velocity of this body will get by this Jx by ICM. If I apply my impulse at very less distance from the center of mass, it will not rotate with very high angular velocity, rather it will rotate with less angular velocity. If I apply it here, so it will rotate with like this maybe. If I apply here, it will create more angular momentum for the body, so it will rotate very fast, like this it will rotate. Okay. Now what will be the total energy for this body? If the body is moving as well as it is rotating with respect to the center of mass omega. Total energy of combined motion. Total energy will arise due to the translational motion as well as the rotational motion. So for translational motion, the kinetic energy will be half of m into v square, plus due to the rotation also it will have some energy, that is called rotational kinetic energy, that is half of I into omega square. So this is the total energy for a rotating body with distributed mass. If the mass is very small, or if it is a particle mass or point mass, the total kinetic energy we consider only half of mv square, because the I or the dimension of the body is so small, we can assume that entire mass is concentrated at the center only, or the center of mass only. So I will be 0 in that case. That is why total kinetic energy is becoming half of mv square for a point mass. But for a distributed mass body, if it is rotating as well as it is having the linear velocity, the total energy will be half mv square plus half of I omega square, or I center of mass omega square we'll call. One more interesting concept. Now let's suppose this is x and y axis. One distributed mass body is like this. Its center of mass lies here, C, we will write C. Now with respect to this coordinate, origin, center of mass is lying at distance RC vector from the origin. Now if I have to find out, suppose I am telling that at point P, what will be the velocity of the point P? How can I find out? So with respect to the center of mass, the point P distance vector Rp with respect to center of mass, or the relative distance of the point P with respect to center of mass. Now we can write that Rp with respect to origin, that will be R of center of mass with respect to origin plus R of P with respect to the center of mass. That is just a vector concept. So in this triangle, this is the center of mass, this is the point P, and this is the origin. So this is the original distance vector from the origin of this point P. So this is Rp with respect to O vector, and R center of mass with respect to O is this vector, and with respect to the center of mass it is located at Rp with respect to center of mass. So this is Rc with respect to center of mass. So basically it is just a vector addition. Wait. If we differentiate with respect to time, we will get that similarly V of P with respect to origin, or the absolute velocity with respect to the ground frame. The origin, we are considering it is a ground frame, that is V C with respect to O plus V of point with respect to the center of mass. Now what is that? Let's understand that. With an example, let's understand that. This is very important concept. You should note it down. Now let's say there is a circular disc. It is rotating with respect to the center of mass with angular velocity of omega. Let's say omega is 2 radian per second. This is the x-axis and this is y-axis, and outward of the board is z-axis. I have to find out the velocity of this point. Of suppose this point, I have to find out the velocity, this point. So the radius of this disc is given as, R is given as 1 meter. It is rotating like this, and while rotating it is also moving vertically upward or to the direction of the y-axis with velocity of 2 meter per second. We will write j cap v. So for this point P, which is located here, I have to find out what is going to be the velocity of that point. So see, it is a combined motion. So this is rotating as well as this is moving upward. So this disc is rotating and it is moving in the y direction. So you have to find out the velocity of the point P. Now for the center of mass, what is the velocity with respect to the origin? You got it already, that is 2j meter per second. Now basically I have to find out Vp with respect to the origin. What is going to be the absolute velocity of the point P with respect to the origin. Now see, this point P is located here at this point. If I tell that the angle is 45 degree at this point, you have to find out the velocity of the point P. So what is going to be the velocity of the point P with respect to origin? That is, will just velocity of the center of mass with respect to origin plus velocity of this point with respect to the center of mass. So see, it is divided into two parts. One is purely translational motion of the center of mass, another is purely rotational motion. So Vp, or velocity of point P with respect to the center of mass means I am sitting on the center of mass of this body and I am seeing how the point is going to move or how the point is moving with respect to this point. The meaning of this term is velocity of point P relative to the center of mass. That means some observer needs to sit at the center of this disc and he needs to see how this point is moving. That means I am already inside a moving system. I am seeing how the other point is moving with respect to me, and somebody standing outside or somebody standing in the ground, he will see that my velocity is getting added to the velocity I am seeing that particle is moving with respect to me. This is the one. So this is already known, that is 2 into j. Now this is unknown. We have to find out this one. See, r is 1 meter and omega is 2. So right now we have already considered the translational part of this combined motion. Right now only we are left with, that is the rotational motion. So this part we have already considered. It is moving. Okay, let us have some. So right now we will consider the second part of it. This is the first part, this is the second part. I am standing here, I am seeing how this body is moving. If I am standing here, I will see that this velocity of this point is perpendicular to the distance vector from the center of mass in this direction. And that velocity is going to be r into omega. What is r? R is 1 meter, omega is 2. So basically this is becoming 2 meter per second, but the direction is this direction. So that means the velocity of this point with respect to the center of mass is this direction with 2 meter per second. Now see, this direction is properly coinciding with the direction of the 45-degree angle, but in towards this direction. So this direction, so I can write out that the magnitude of this vector is 2 meter per second directly, but I need to multiply with the unit vector in this direction, which is going in this direction. So if one vector is there and making angle 45 degree, the unit vector in this direction is I cos 45 plus j sin 45. But right now I am moving in the opposite direction. So it is negative y as well as negative x. So I will just put a minus. So minus I cos 45 minus j cos sin 45. That is the unit vector in this direction. So that is our velocity of point P with respect to the origin. So 2j plus or minus 2 by root 2, that is root 2i minus root 2j. So it is basically becoming minus root 2i plus 2 minus root 2 into j. That is the velocity of point P with respect to the ground frame or with respect to the origin. Okay. Now we will see the combined angular momentum for a rigid body. Let us draw a diagram. Suppose this is a circular disc or some circular body having distributed mass. Its center of mass lies here. Center of mass, COM we will write. Now with respect to some particular fixed point outside, what is going to be the angular momentum of this body? So let's say this body is constituted of many small masses, we can assume. Now let us assume one very common mass, let's say I mass or ith mass, Mi. We'll write Mi at here, this point maybe. So suppose this is the origin. With respect to this origin, I have to find out the angular momentum for a rigid body. See, I can find out angular momentum for a rigid body with respect to any point. If I tell you, let's find out angular momentum of this body with respect to center of mass, you will write I is I into omega, that is the angular velocity, that is angular momentum with respect to the center of mass. So what is the distance vector of this center of mass, let's say it is RCOM, RC we will write. And with respect to center of mass, the distance for this ith mass is I with respect to C we will write. So R for this ith mass with respect to the origin is going to be the vector sum of center with respect to the origin plus I with respect to the center. That is purely vector addition. Now similarly we can write that velocity of the ith particle or ith mass with respect to the origin is summation of center of mass with respect to origin plus velocity of ith particle with respect to the center. Now let's say the mass of one ith particle is m into I. Now what is going to be the angular momentum with respect to this point O? Angular momentum of this body with respect to point O, with respect to any point O, is mi into ri cross vi with respect to the origin. Ri with respect to origin cross vi with respect to origin. Now total angular momentum will be the summation of all small angular momentum for all these bodies, all these small masses, and this is the angular momentum of this body with respect to this point O. Now let us put these values here. Summation of mi rc with respect to origin plus ri with respect to center cross v center with respect to origin plus vi with respect to center. Now we will get 4 parts. One is RC with respect to O cross VC with respect to O plus summation of MI RC with respect to O cross VI with respect to C plus MI RI with respect to C cross VC with respect to O plus the fourth term will get MI RI with respect to C cross VI with respect to C. Now some terms will be 0. What are those terms? See, this term is a summation. See, if I remove this bracket, it is just MI RI summation. So with respect to the center, the mass is equally distributed. So the net first moment of all those masses will be 0. So this term will be 0. Now similarly, I can tell that, see, this is MI, RC is okay, VI is there. So summation of all the velocities with respect to the center of mass, summation of all velocities with respect to center of mass is evenly distributed. So this term will also be 0. So we are left with 2 terms. First term is summation of MI RC with respect to O cross VC with respect to O plus summation of this part MI RI with respect to C plus VI with respect to C. Now this term is basically the angular momentum of this body with respect to O. If any mass is moving with velocity V and if the position is R, m into R cross V is the angular momentum with respect to this origin. So this is also the angular momentum of the center of mass with respect to the O will tell. Plus, see, this part is the net angular momentum with respect to the center. See, all parts is related to the center of mass. So this we can tell the angular momentum with respect to the center of mass. So see, net angular momentum with respect to one particular point is the summation of the angular momentum of the center of mass plus the angular momentum with respect to the center of mass. So total angular momentum with respect to any fixed point will be the angular momentum of this body or angular momentum of this body, or COM will write, plus considering it is a particle mass, plus the angular momentum with respect to the center of mass. So this body is moving with velocity v as well as is rotating with angular velocity omega. So this with respect to the center of mass, the body with respect to the center of mass. Now this concept may seem very difficult, but we'll understand it through a problem. Now let's say one disk or one sphere, let's say one sphere is rotating with angular velocity of omega and with a linear velocity of omega r. So this is a combined motion because it is rotating as well as moving forward, just like a sphere rotating, just like a cricket ball rotating or a football is rotating and is moving. So I, and the mass is m, radius is r. What is going to be the angular momentum with respect to the point where instantly it is touching the ground? So with respect to this point, I have to find out what is going to be the angular momentum. So instantaneously this sphere or this rotating body will rotate with respect to this point for this instant only. So net angular momentum with respect to this point is the sum of angular momentum of the center of mass plus angular momentum of the body with respect to the center of mass. Now this is going with angular velocity omega and this is moving forward with translational velocity omega into r. So we can easily write that with respect to this point, this O point, one particle of mass m is moving with velocity omega into r at distance r. What is going to be the angular momentum? M into r cross v, r cross omega r in this case. See, r and omega are perpendicular, so cross product will be just r into omega. So we will write m omega r square. This is the LCOM. Because we are assuming the entire mass is there and it is going with velocity v or omega r. So first part is m omega r square will write. Plus now I have to find out what is going to be the angular momentum of the body with respect to the center of mass. That means translational motion of the center of mass I have already considered. Now I will forget it is translating. Now I will only consider the rotational motion. Right now I am sitting here, I am seeing that it is rotating with angular velocity of omega. Translational velocity I have already considered here. First part and second part. So if one body, one rigid body is rotating with respect to this axis, what is going to be the angular momentum? I into omega. So I into omega. What is I for this sphere, solid sphere of mass m and radius r? 2 by 5 into m into r square into omega, that is angular momentum. So we'll write that m omega r square plus 2 by 5 m r square into omega. So net angular momentum with respect to this point is going to be this plus this, that is this is basically becoming 7 by 5 m omega r square. That is the angular momentum with respect to the fixed point O, or instantaneous fixed point O is going to be the angular momentum. Now if I tell you what is going to be the direction of this angular momentum, so direction of the angular momentum is with respect to this point or this O, instantaneously or for this instant it is rotating like this. This is rotating like this. So it is like this. So what is the direction? The direction is inward or inside the board. So we can write, as of now, if axis is not defined, I will define the axis and z axis will be outward, so it is minus k direction, or we can write inside the board, inward, or minus k cap we can write. I hope this part is clear because this is a very complex concept. Maybe initially you will find it very difficult, but with time, as you know more and more and as you solve problems, it will be very easy to you, and once this concept is absorbed, you will find it very easy to go forward and how to approach a particular problem. Now let's look at another problem which involves the concept of combined motion of translation as well as rotation. So this is a rod of mass m or scale of mass m and length L. It is freely lying on the table and one impulse is given at one extreme end of the rod. You have to find out why this rod will complete one revolution with respect to its center of mass how much distance its center of mass will go forward. So if I am giving it one impulse at extreme end, it is going to move like this. So while it completes one complete revolution, you have to find out the distance its center of mass covers. So it is going to be moving like this. If I give an impulse here, it will go, it will move, it will complete one revolution. By the time it will complete one revolution, how much distance from the initial position it goes in the forward direction. So this is a problem of combined motion. So first of all, the first idea or first motion we will consider, that is translational motion. Translational part of the combined motion. Translational part. If J impulse is given at any part of the body of mass m, it is going to move with J by m velocity. Or we can tell that J impulse is going to change the momentum of the body, or the linear momentum of the body. Is right now it is at rest, so initial momentum is 0, so change in momentum is basically equal to J. So V is going to be J by M. That is our first equation. Now the second part will go, that is the rotational part. J is given, impulse is given, so it is going to move with angular velocity omega, as well as it will go forward. This is V we have already found out. Now omega, what is the value of omega? See, with respect to the center of mass, what is the angular momentum? It is given to the body, J into the distance from the center of mass, that is L by 2. That is the angular momentum given to the body, or this much of angular momentum will change for the body. So initial angular momentum is 0 because initially the body was not rotating, not translating. So initially omega was 0. Right now, if it is getting one angular velocity, then angular momentum will be I into omega minus initial angular momentum is 0. So change in angular momentum is equal to I into omega. Now what is this I? I is, it is rotating like this with respect to center of mass. So I will be the moment of inertia with respect to the center of mass. So what is the value of I with respect to one middle point of a rod of mass m and length L? M L square by 12. So M L square by 12 into omega, that is going to be j into L by 2. So we can find out the value of omega here. The value of omega 6j by ml, that is the value of the omega, that is the second equation. Now for one revolution, how much time it will take? So in that time, the center of mass will go forward with this velocity. So this is the angular velocity 6j by ml. Now for one revolution, it needs to cover 2 pi angle. So one revolution, how much time it will take? Suppose delta t time it is taking for covering 2 pi angle with this angular velocity of omega. So 2 pi by omega will be the time when it will complete one revolution. This is the angle covered in unit time. So net time for one revolution is 2 pi by omega. So that is 2 pi by 6j by ml. So that is basically ml pi by 3j. That is the time taken for one revolution. So while it will rotate, so this time is delta t is ml pi by 3j. So till this time, this will move also in the forward direction. So what is the distance? V into delta t. So in this time delta t, it is also moving forward with the velocity of this amount. So what is the distance it will cover? So j by m will write the value of delta t ml pi by 3j, and we are getting mm will cancel, jj will cancel, so it is L pi by 3, that is the distance covered while it will rotate once. I hope you understood this problem. This is a very interesting problem. Maybe initially you will find it very difficult, but with time, as you know more and more and as you solve problems, it will be very easy to you, and once this concept is absorbed, you will find it very easy to go forward and how to approach a particular problem.